Hello and welcome. In this video, we're going to talk about Rolle's theorem and the mean value theorem for derivatives. So let's go ahead and jump in. If we have a continuous function on a closed interval and it's differentiable on the open interval, and third condition, what we get when we plug the endpoints of a given interval into that function are the same, then at some point in time the derivative has to have been equal to 0. So if we're being asked to apply Rolle's theorem, specifically what we're really being asked to do is figure out what happens when I plug in the endpoints and whether or not the thing that I get the number that I get when I plug those in is the same. So let's go ahead and check that first. This is going to be 1 minus 3 plus 2. That's going to be 0. If I plug in 2, I get 4 minus 6 plus 2. That's also going to be 0. So since these are the same, that means that Rolle's theorem applies. Now, this question doesn't ask for it, but let's just verify that we can actually find that derivative. So since those are the same, Rolle's theorem says that there has to be some value that makes the derivative equal 0. So let's find the derivative. The derivative would be 2x minus 3. And if we substitute 0 in for f prime of x, we can get that that specific value would be 3 over 2. So you either need to be given an interval on which you're checking, or occasionally I have seen textbooks ask you for the zeros. So you're going to, if that were the case, you would figure out the two values that make this 0 by factoring, and then you would use those as your endpoints. Let's go ahead and move on and talk about the mean value theorem, which is really the big part of this lesson. Before I tell you what the mean value theorem is, I want you to look at these 6 graphs below, and I want you to think about if that dotted line is the secant line, whether or not you could draw a tangent line that is parallel to the secant line. So go ahead and pause the video and think through that for just a minute. All right, hopefully you've had time to think about that. I could draw a tangent line here that is parallel to that secant line. If I tried to draw a tangent line here that's parallel, I have an issue because there's a hole in the graph. I could draw a tangent line here. It would be horizontal, and I just want to point out that the derivative would be undefined here. And here it looks like, it's not indicated on the graph, but it looks like there's a vertical asymptote, so I'm going to have some issues drawing a tangent line here as well. If I look at 5, I could draw one here, I could do one here, and one here. If I look at 6, I could draw a tangent line that is parallel, if I could draw a little bit better, that is parallel to that secant line in multiple places. So the only 3 that I could not do that on were these 3 right here. And what was going on in those 3? Either the derivative was non-existent because of a discontinuity, or there was a sharp turn happening. So it seems like in order for us to be able to have a tangent line that's parallel to the secant line, we need to have a function that is both continuous and differentiable. Let's formalize this with the mean value theorem. Before I describe the mean value theorem in mathematical terms, I want to walk you through what it actually is talking about in a more simplified way. If I were to get into my car and drive from here to Disneyland without stopping, never hitting a traffic point where I had to come to a full and complete stop, we could say that my drive was continuous. And if I was to tell you that the average speed on my drive was 65 miles an hour, at some point in time, I needed to be actually going 65 miles per hour. In order for the average to be 65, there were moments where I was going above that and moments that I was going below that, which means at some point in time, I had to actually pass through 65 miles an hour if we're talking about something continuous. What that means is my average rate of change over the entire drive was at some point actually the exact speed I was driving at. So how this extends to calculus is we can say that as long as we have a function that is continuous and differentiable, at some point in time, at some value c, there must be a moment where our derivative, or our instantaneous rate of change, is equal to our slope of our secant line, or our average rate of change. So I'm going to talk about the derivative being the IROC, the instantaneous rate of change, the slope at the exact moment. That needs to be equal to, at some point in time, the slope between the 2 points, or the average rate of change over the whole interval. And I'm going to refer to that as the AROC. So the mean value theorem says as long as I have a function that's continuous and differentiable on the interval, at some point in time, my AROC and my IROC are going to be equal to each other. So let's look at some examples here. The first thing I need to look at is f in number 1 continuous and differentiable on that interval? And the answer is yes. We have a parabola, which is continuous, and this is also differentiable on the interval we're talking about, so MVT applies here. If MVT didn't apply here, then you would say it doesn't apply, and you would say why it doesn't apply, and that would be all you could really do there. So let's find our instantaneous rate of change first. That really just means find the derivative. This derivative is going to be 2x minus 2. Then we're going to find our average rate of change, and here are the x values that we're going to use. So we're really looking for f of 2 minus f of negative 3 over 2 minus negative 3. If I plug 2 into my function, I'm going to get 4 minus 4 plus 3, that's 3. If I plug negative 3 in, I'm going to get 9 plus 6 plus 3, so 15. So our average rate of change is going to be equal to negative 3. Sorry, this should be negative 18. 3 minus 18 is negative 15, divided by 5 is negative 3. So according to the mean value theorem, there is some value c, or some x value, that would make these two things equal. So let's go ahead and find that. If I add 2 to both sides, I get 2x is negative 1, so x is negative 1/2. This question asks us for what c value, so c is negative 1/2. I encourage you to pause the video and see if you can work through number 2 on your own. I'm going to give you a little hint. I would actually rewrite this point 2 as a fraction 1/5. So hopefully you have had time to work on this. Number 2, this function is continuous and differentiable. So MVT applies. So I'm going to find the instantaneous rate of change. The derivative is going to be negative x to the negative second, since this is x to the negative first. And I'm going to go ahead and rewrite that as negative 1 over x squared. The average rate of change is going to be f of 2, which is 1/2, minus f of 1/5. If I have 1 over 1/5, that's going to become 5. So this is f of 2 minus f of 1/5 all over 2 minus 1/5. And if I divide this by 2 minus 1/5, 10/5 minus 1/5 is 9/5. So I really have negative 4.5, which is negative 9 over 2. And I'm going to multiply by the reciprocal here. So these 9s are going to divide out. So the average rate of change is negative 5 over 2. Based on the mean value theorem, there has to be a moment where these two things are equal. So we can set this up and cross multiply, or, oops, this should be negative also, cross multiply or isolate x squared. So this is going to give us negative 5x squared equals negative 2. So x squared is 2/5. So x is plus or minus the square root of 2/5. Since we are looking only on this interval here, the only answer we can include for our c value is the positive version. One more example, and then we're going to wrap up this section. I really encourage you to pause this video and try and work through this last one on your own. I know that the trig makes it automatically a little scarier, but I bet you can. All right, hopefully you have paused the video, and now you're just checking over your work. We're going to note that f is continuous and differentiable. So MVT applies. So the very first thing I'm going to do is find the derivative of this. The derivative of cosine is negative sine. Then I'm going to find the average rate of change for cosine. So I'm going to plug in cosine of 3 pi over 2 minus cosine of pi over 2 over 3 pi over 2 minus pi over 2. Well, cosine of 3 pi over 2 is 0, and cosine of pi over 2 is 0, so this is all going to be 0. So according to the mean value theorem, I want to know when does negative sine of x equal 0, which was the average rate of change. Well, sine is 0 at 0 and pi and 2 pi. The only one of these that is actually within this interval is pi, so here this c value is pi. So let's recap what we covered in this section. First, we talked about Rolle's theorem and how Rolle's theorem says if we have a continuous and differentiable function and the value at both of the endpoints of some interval are equal, at some point the derivative was 0 within those bounds. The highlight of this video, the most important thing, is the mean value theorem. The mean value theorem says that if we have a continuous and differentiable function, then at some point in time, the derivative will equal the average rate of change. So you can find both of those values and set them equal to each other to find the c value that makes the derivative equal the average rate of change. So go ahead and write down any questions you have. I look forward to supporting you on this. Thanks for listening.